Alright, this lesson is focusing on dilations and similarity in the coordinate plane. Objective, I've learned to apply similarity properties in the coordinate plane. And just to kind of review, refresh memories about what a dilation is, and that's misspelt. Dilation should actually be D-I-L-A-T-I-O-N. A transformation that changes the size of a figure but not its shape. The pre-image and image are always similar. That's going to be kind of important to remember. Pre-image and image. Right, so let's say that this is a pentagon. We'll call this A, B, C, D, E. Right. The way we kind of denote this dilation, if this is our pre-image, this is kind of where we started. Okay, if this is our pre-image, this one would be our image. Okay, so something to remember is the pre-image is always the original picture, and then you go into the next one, which is called the image. All right, and the way we kind of do this is we put a little apostrophe next to each letter, and we call that A prime, B prime, C prime, D prime, and E prime. It's just another way to kind of note which point corresponds with which one, but it's telling us that they're different because this would be a larger, in this case, this would be a larger image than our pre-image. Okay. Now, when we make a dilation, we have this thing called a scale factor, and it describes how much the figure is either enlarged or reduced. Okay, so looking at this first example, I know the triangle ABC is similar to the triangle DEF, and it says what's the scale factor used to go from triangle ABC to triangle DEF. All right, and then so that means we're going to go from 2 to 9. And since that doesn't reduce, that is our scale factor. Our scale factor is 2 ninths because BC would be correspond to EF, and so that would be 2 to 9. Sometimes you might have to reduce. In this case, we didn't. All right, now for a dilation with a scale factor, some scale factor k, you can find the image of a point by multiplying each coordinate by k. So if I have these points A, B, and I want to create a new image, I would just simply multiply k times each coordinate. So k times A, k times B. As long as my center of dilation has to be at the origin, which for us, that's what we're going to be focusing on. So here's our first example. Triangle JOY is graphed below. And we want to dilate it by a scale factor of 3. So we're going to take each point. In this case, we really want O is the only one we want to do to answer the problem, but I'm going to show you how to do all 3 of them. So I would take my coordinates of O, which would be 3, 2. That's the original coordinates. And I'm going to take each one and multiply by my scale factor of 3. So my O prime would actually be 3 times 3 and 2 times 3, which is going to come out to 9/6. So O prime would be 9/6. So that's going to go from 9 up to 6 right there, and I'd call that O prime. All right. Just kind of extra practice, let's go ahead and do that with J. J is at 0, 0. J prime, if I multiply anything times 0, that's going to give me just 0. So this one doesn't move. This is J and J prime are going to be the same point. If I look at Y, that's at 3, 0. So Y prime is going to be 3 times 3 and 0 times 3. So that ends up being 9, 0. So that would be here. Right, now, so I'm going to go ahead and just connect those. So you can see how by scale factor of 3, how that enlarges the original triangle. All right, this next example, I have this triangle DFG, and D is at 2, 4. So there's D. F is going to be at 4, 8. And G would be at 6, 4. Right, and then it says we want to dilate by a scale factor of 1/2, and we want to look at G prime. So I'm going to take G, which is at 6, 4, and I want G prime, so I'm going to have to multiply each one by 1/2. Okay. So G prime is going to be 1/2 times 6, or 6 times 1/2, which is 3, and then 4 times 1/2 is 2. So that is my G prime. If I were to graph that, that's where G prime would go. Alright, now on this one we have to figure out what the scale factor actually is. So they gave us the pre-image and the image. We have to figure out what happened to the picture. So I'm going to take my C, won't work because that's both at 0, 0. That's really not going to get me anything. So I would look at maybe A prime and A. So A, my coordinates for A are going to be 4, 8. A prime is 2, 4. Okay, so I want to look to see what happened. And I'm going to put the image on top. So I would do 2 over 4. So I took the x values from each one, and that would reduce down to 1/2. Okay, and just to show you that it's the same thing if I did the y's, and I did 4 over 8, that is also 1/2. Notice that I put my image as my numerator and the pre-image as the denominator. That's going to be very important because what happened is the picture actually got smaller. So my scale factor would be just 1/2. This last little example that we need to look at is going to actually take the coordinate plane, and we have to prove that these two shapes are similar. So remember that we can use either AA, SAS, or SSS to prove that these are similar. I'm going to choose to use SAS because I have this common angle right here at A. Right, so I know A is equal to A. That would be our reflexive property. Okay. Then I'm going to need to look at the sides. Remember, the sides have to be proportional. So I need to figure out what the distance of AB is, the distance of AD, and then I also need to know the distance of AC and AE. Right, so I'm going to use Pythagorean theorem. You can use the distance formula to find these lengths, but I want to kind of create these right triangles here. So if I go up 2 and over 2, all right, Pythagorean theorem would tell me 2 squared plus 2 squared is going to be 8. And then I have to take the square root of that, so this is going to be the square root of 8. If I look at AD, I count these 1, 2, 3, 4. And I go back 4. Right, so that's going to be the square root of 4 squared plus 4 squared, which is going to be the square root of 32. Right, then I want to do the same thing with AC. So in this case, I go 1 and over 2. So that's going to be the square root of 1 squared plus 2 squared, which is going to equal the square root of 5. All right, and then I have to look at AC, so that's 2, and then if I count this back, it's going to give me 4. So that would be the square root of 2 squared plus 4 squared, which would be 20. Right, now remember, the sides have to be proportional. So if I'm looking at the square root of 8 over the square root of 32, does that equal the square root of 5 over the square root of 20? Right, so if I multiply here and here, square root of 20 times 8 is going to give me the square root of 160. And then if I take 32 times 5, right, that also comes out to 160. And they're equal. So I would say yes, the sides are proportional. So that means then that triangle ABC is similar to triangle ADE by SAS.